If atoms end up sharing more than one electron, they can form double and triple covalent bonds. So if a single bond is 2 electrons, these 4 electrons would be a double bond, and you can see how with oxygen, having 1, 2, 3, 4, and these shared 4, that's 8 electrons. Nitrogen has to share 6 electrons. So that's a triple covalent bond, and so it has only 2 other independent electrons in its valence shell for that total of 8, for that octet rule to be in play. Now I've been using the Bohr model to show all of this, but it's actually easier to use something called a structural formula, where you use a single line in place of the shared pair of electrons. So here's hydrogen, so all the ones from before with that double and triple bond shown as the double single line or the triple line. And these are called their molecular formulas, so you can see the H2 and the CH4 and the O2 and the N2 with that subscript. So many ways to show the same thing. Now, as we know from life, this whole sharing thing works just fine until bullies enter the picture. What if one atom's nucleus pulls a lot harder on those shared electrons than the other nucleus? Well, they'll still share, but unequally. So now we're considering polar covalent bonds, the unequal sharing of electrons. To visualize this, we need to adopt a different view of the atom, one where electrons are free to move in electron clouds and not on fixed orbits. Oxygen here is the notorious electron bully. In geek speak, we say that oxygen is more electronegative than hydrogen. You can look up electronegativity in a chart. The more similar the electronegativities are, the more equally the electrons are shared between them. But between oxygen and hydrogen, very unequal sharing. So if we put them together in water, the electrons are going to spend a lot more time near the oxygen nucleus than the hydrogen nucleus. And the result's going to be something we call dipoles, where the oxygen behaves as if it's negative, the oxygen side, and the hydrogen side behaves as if it's positive. The result is what we call a polar covalent bond. So you're looking at 2 polar covalent bonds here, one between each hydrogen and oxygen. And the resulting molecule is called polar. The boundary of every cell in our body is defined by the difference between polar and nonpolar molecules. Polarity is a huge deal in biology. So looking at a simpler picture of this water molecule, if you're thinking a lake or a stream and you're putting a bunch of waters together, they're not going to sit around in this orientation. They're going to start to, let's see if I can grab one, turn and rotate so that positive hydrogens face negative oxygens, and the result are these little bridges are going to form, and those bridges are called hydrogen bonds. And so they'll reorient themselves. And so you start to form this lattice-like network. And if you put salt in water, the little polar bits of the water molecules are going to start to isolate the sodium ions and the chloride ions, and that's why things can dissolve in water. So this is not a long-lasting bond like covalent bonds, but many hydrogen bonds together can really start to shape us. They hold together our 2 double helical DNA strands. They're responsible for most of the folding that shapes proteins into little working machines. Hydrogen bonds normally involve the hydrogen of one molecule being attracted to another molecule. So if you put hydrogen with another hydrogen, it's not going to form a polar bond. Hydrogen next to oxygen or nitrogen will form a polar bond. So if you see hydrogens near those 2 atoms, that's where you're going to start to see those parts of the molecules, the parts with the hydrogen and oxygen covalent bonds or the hydrogen-nitrogen covalent bonds, they're going to start to attract or repel other polar parts of the same molecule or other molecules. Why is hydrogen so special in all of this? Why do we call it a hydrogen bond? Well, its single proton tends to really not share electrons equally with most other atoms. So you tend to see it involved in the parts of the molecules that become polar. So that's where we're going to stop today. And there's so much cool stuff to come once polarity is involved.